Hello and welcome. Did you start the thing? Okay. Hello and welcome. I'm Radu. This is my colleague Rafał. We work together at Sematext, where we do consulting, training, production support for Solr and Elasticsearch. We're also working on our centralized logging and monitoring products. And today, we're going to talk about Solr and Docker. And basically the agenda is we're going to talk a bit about the architecture of Docker and the alternatives, and then we're going to do a demo. That's going to be the biggest chunk of how you can run Solr on Docker. And then finally we're going to share some performance numbers and some operations gotchas. So what is Docker trying to solve? Basically, if you start from like the typical bare metal setup, you have a bunch of big boxes, and then if you have smaller apps, you're going to have to either over provision like crazy, or you need to run multiple of those apps on a bigger box, and then you have a problem with limits between them. Also, you have your own bare metal, and then the testing bare metal, and then the production bare metal, which may differ, and then configuration drifts, and then disasters.
Apocalypse.
Yes, right. So this is what Docker's trying to solve. You have one container that you can run everywhere. You know the drill. And so basically, with bare metal, you have the operating system sitting between the hardware and your application, right? On a VM, if you want to isolate this way, then you have the VM running on top of a hypervisor. So then, you obviously have the overhead of the guest OS. Docker runs on top of Linux containers, which is like operating system level virtualization. So you share the kernel, it will start much faster, and you have much less overhead in terms of memory. And we'll talk about performance a bit later on. We also wanted to bring unikernels into the discussion. For those who are not familiar with them, these are like specialized stripped kernels, which are designed to run one process only, and which is how you'd use Docker typically. And the use case is somewhat similar. Also, like Docker acquired a company who contributes to the unikernel ecosystem, and basically have multiple types of unikernels. Some are stripped down from NetBSD. These are called the rump unikernels. Some of them are built from scratch, like Mirage OS or OSV. We won't spend too much time on those because they're not, I think, mature yet to use in production. But I thought it's interesting to follow their development, because the promise is to basically bring the best of all those worlds, because because they're actually VMs running on top of the hypervisor, they bring the limits that you normally get from traditional VMs. But because they're stripped down, they start, and you have the flexibility and the performance that you normally get from containers. And actually, from the performance, some of them you can compare them to bare metal, because if you run a unikernel, then you don't need to care about things like multi-user. You don't need to care about separating the kernel from the user space. So then you can do a lot of tuning in terms of, for example, network and I/O performance. So next we're going to show you this demo, and this is just a slide showing you the gist of the commands that we're going to run. Basically, we're going to show you how to start the official Docker image for Solr. We're going to talk a bit about port forwarding, networking in Docker, how you'd use volumes, how you'd link containers, how you would cap resources like CPU and memory and things like that. So
demo time.
Computer guy.
Give me your mic,
So
and
you're just gonna hold it like this?
yes, and I will gonna hold it for you.
This is gonna be funny.
Imagine you're on stage and you're singing.
Naked.
Okay, let's forget the naked part.
Okay. So first things first, if you just want to run Solr, you can simply go like docker run Solr being the image name. This is the official container. We just type Solr. Otherwise, you'll be like username / image, and then the version name, which in this case is latest. In our case, it starts right away because we have the image itself cached. Otherwise, you'll just download it and start it for you. So, and then you'll see the logs on the standard output. However, if you want to connect to Solr, your enter is in the worst place.
Sorry for the Polish language, by the way.
Yeah, it says something, which looks like an error to me, right?
Yeah,
So,
it just can't connect.
We don't want errors. So the problem here is we don't forward the port, right? So we'll need to stop the container, but I'm just going to copy paste the port command over here. So we stop the container by just Control-C, right?
By the way, we didn't tell that, but all those commands are already on GitHub. You've seen that. You can just replay the demo. So just in case you are wondering while we copy pasting, just not to make mistakes.
Yeah, because demo gods are already angry with us, as you could have seen. We don't want to, yeah. So this will forward the port, right? And so now we run it, and normally, if we refresh this page, here you go, we have Solr. Right?
Yay!
Yes, thank you. Okay, so now I'm going to give it a name because no, I'm not going to give it a name. I'm gonna not start in foreground because that just sucks. You don't want to attach the thing to your terminal, right? So I'm gonna start it as a daemon, right, with -d, and this will go to background. So now if I do docker ps, it's gonna show me the very nicely named modest Newton image that it created, right? It's a kind of an arbitrary name.
Nice to meet you, I'm Rafał.
Right, so I'm gonna stop this guy. This is what I want to do, right? Stop this guy, and then I'm gonna stop it. I'm gonna stop. I'm gonna use the container ID just because I can. Right? Then I'm gonna remove it, right?
Yeah.
Docker.
Kill it.
rm.
Copy paste for the win.
Yes, that is a handy thing. So now I'm gonna start with an actual name that I can identify. Because if you start more containers, you're gonna need that. These Macs.
Copy pasting is also hard.
Yes, it's a skill. So you do like -- name, and you put your name there, Lucene Revolution.
Single Solr.
Right? And now if I do docker ps, I have the nice Lucene Revolution name over here. So next, okay.
My hand hurts.
So next I'm gonna stop it, right? And I'm gonna use the Alpine distribution thingy. So I did PS, right? And I'm gonna stop.
Mm-hmm.
And just because I clean up after myself, I'm gonna do rm2. And now, because normally the official image runs on top of Ubuntu, which is nice for testing around, but it can be quite bloated. So you can use the Alpine one, which is just by changing the version to like 6.2 Alpine in this case. So now if I run it, it's gonna be on top of the kind of stripped down sort of Linux distro that is Alpine. So here it is.
I can clean up.
You can clean up? Okay.
Yes. So it will be easier. I have my mic here. So now, when running the official Solr image, official Solr container, you usually want to do more setup before really going into production. Like, for example, set the heap. And we are allowed to do that by providing a script that will be placed in a certain directory inside the container. We can mount the script that we'll create during during start of the container, so we don't have to rebuild it and keep up with the versions of the container. We just need the script. Let me clean up after Radu. Sometimes do that. I can't help myself.
You said you want to do it.
Shh. Don't. Not now.
It's recorded.
The thing I want you to show you actually here is the script that I will use. It's called Lucene Revolution set heap. It's a very simple script. It uses bash. And what I do is I take the original solr.en.sh file and I copy it to inside the container. Of course, I do it. To copy it, make it a copy out of it, I replace the Solr heap property, which controls the heap of Solr during startup, the standard solr.in.sh file, as we are used to when running Solr in production. I replace the heap with the one that I want to have, like here 1 gig, and then I just do a grep to show that in logs, and that should work. However, what I need to do is I need to provide the mounting point for the script to actually run. The mounting point that Docker allows us to use is, let me clear that up, is located inside the Docker entry point initdb.d directory, and we can put the script there, basically. So what I did here is I said -v, and from my current directory, where the script lives, actually, here, right? We have that script. I say, I want that script to be put into / docker entry point initdb / and the name of the script, just like just the same name. It can be different, it can be the same. What Docker will do in that case, it will, when the container is started, before running this application, it will just go through the scripts in that particular directory and just apply them before running Solr. So we should have our Solr heap adjusted properly. Let's check that out. First of all, the first thing that we can check is actually how much memory by default Solr has. So we can see here it's 512 megabytes, right? Not sure if it's perfectly visible. But that's how it works. If the gods of demo will help me, and everything works well, we have 1 gigabyte here. So it seems that this thing worked. However, I told you about that something should be placed in the logs. And there are 2 ways, actually there are multiple ways to look at the logs. We can take something that provides us with the capability of gathering the logs from Docker and sending it to a centralized host, like our log agent does. We can use Kitematic UI. There is something that comes with Docker. It's called Kitematic, and we can basically launch it. We can look at our LR Solr heap container. We can go through the logs and see what's happening there. But there is also a possibility to use a command line. So how to do that? We take the Docker, we say logs, and we specify the name of the container we're interested in. LR Solr heap. I think that's what it was called. And you can see that on the output of that, Docker really gave us logs from Solr. And on top of the log, we can see actually what was happening here. So in the opt Docker Solr scripts, Docker entry point, we run that particular script put inside the Docker entry point initdbd directory, and it got us the grep we were looking for. So everything was working as it should. Let's stop this container. I'll do that just by stopping it, clearing that up. The thing is that that's not all. whenever running containers in production, usually we want to limit and give the constraints. Why? Because we usually won't run a single container on top of our hardware. It doesn't make sense, really, to do that. So what we can do with Docker is that we can limit the number of CPUs, the quota of the CPUs, the memory that Docker is allowed to use, and just put it whenever we launch the container. Let me show that. For example, if we would like to run the command and give Docker 1 gig of memory for the container, we would specify -d 1 gigabyte. However, keep in mind that on this particular machine, OS X, Docker is still running inside a virtual machine, though I'm using the native approach, so I don't have to run VirtualBox myself. The reason I'm mentioning it is even though I specify the 1 gig constraint for Docker, I still will have 2 gigs assigned to the container, because this is how my Docker is locally set up for the virtual machine. I can show a proof here. If I will it doesn't show it well. Maybe that. You can see here that still the physical memory visible by Solr here is 2 gigs. So, however, on Linux environments, so the environments you would probably take to production when it comes to Docker, that will work. We can also run Docker without swap turned on, which is very important because JVM doesn't like swapping, right? We know that. If you swap JVM memory process, then the performance of that actual application will be just terrible. So what we can do is we can actually turn on swap off basically. Let me just kill that container so it doesn't bother us. So as you can see, I added the -- memory swappiness equals 0, which means that that Docker container shouldn't use swap, and that's another constraint that we can put into the containerization model while running on top of Docker engine. Docker stop. I will stop lots of containers, but usually they don't like to live very long. So let's help them. We also can set the CPU quota and which CPUs are actually going to be used. Like here, I set as -- CPU set CPUs, and I specify which CPUs are basically should be used by Docker. In that case, again, remember this is OS X. Basically, it won't take that into consideration. Although on Linux, when you would run that in production, that would be taken into consideration. But again, I'll just show that the command is actually there, and I'll show you the proof that the Solr container is actually running. We could check the Docker logs, Solr CPU, that the Solr server has been actually started, and it works properly. Again, I'll just stop that container and clear that. I also wanted to tell you a few things about how to execute the scripts that by default come with Solr, because usually when you are running Docker locally, you are using a development mode if you are running on OS X. So it's good to know how to actually work with Solr in that case. So let's start a container here. The same drill. We are using run. We are giving a container a name, and we detaching it from the foreground, so it runs as a daemon in the background. It's clean, please. And now let's execute a standard Docker command that will just execute. Okay, let's execute. Let's run a Docker command called docker exec that will allow us to actually use the commands inside the container itself. What I did here is I specified the user, -- user Solr, which is needed to actually access the data inside the container. Otherwise, errors would happen. I wouldn't be able to access the data. Now, the next thing is specifying the container name I would like to execute the command on, and specify the command itself. Please remember that you actually, when you run an exec on the container, you are already in the home directory of Solr, so where the bins directory and the server directory is living. So in that case, because we are using relative paths, we can just say bin Solr create core getting started. Let's see if the core was actually created. We can do it, of course, by looking at the logs, but to make it easy, we can see that the core is there. So everything works as it should. The nice thing is that we are actually not aware that we are running inside a container because we are just having a path like on normal Linux operating system. The next thing I would like us to see is actually how to run SolrCloud. Because Solr master slave is one thing, then we have SolrCloud, and that brings a set of different challenges for Docker. So first of all, I will run Docker with the Solr image, and I'll run embedded zookeeper here. So again, the same command, similar to what we've seen, specifying the name. I'm mapping two ports here. The first one, the standard Jetty port, 8983, and the second one is the embedded zookeeper port, so 9983, which means that we are running embedded zookeeper. I specified the name of the image, and finally, -c, which will be just forwarded to that command, and the zookeeper will be run with Solr as well. We can check that. Please don't do that to me. Gods of demo were mad. But here we have the cloud. That works. If we would now try to create a core or upload actually the configuration, we should be able to do that. You can see without any issues, I run the docker exec command, giving exactly the same parameters as I did earlier, so the user, and a command that probably most of us working with SolrCloud are already familiar with. So zk upconfig, which means upload configuration to zookeeper. We give it a name, we give the zookeeper host, and of course the directory. Again, assuming that I'm in the opt Solr directory inside the container, I can just say server Solr config set and the configuration I want to use. I'm using a data-driven schema here. Once that's done, we can create a collection. Again, collection API in use, so just specifying curl and waiting for the collection to actually be created. As you can see, everything is done here. If we would go to Docker here and graph, we can see the collection with one shard created. Now let's try to run more than a single node on that particular cluster, large cluster. Okay, don't look because you will know what to expect. Now you can open your eyes. Everything is nice. Docker container was run perfectly fine. I did specify a different port because Docker containers don't actually have the network inside the container. Docker creates a network for a container itself. Now the problem is that we need to forward the port somewhere outside of Docker, so we do that -p switch. Here, because I can't really use two ports, the same port for two different containers, I used a different port for forwarding here. However, and of course, I specified the -z, which means I'm pointing my Solr to a different zookeeper. So I want them to connect to the same, the one that was exposed by the container. You remember, I exposed the 9983 port, right, on the local host. Everything should be running smoothly. So now let's check the logs. Because I have a diff, some ideas that it won't. As we can see, there are errors. Solr can't connect to the zookeeper. That's because the actual container that I run, the second one, is actually not able to see the ports that were exported outside of the container. And that's one of the problems. What we can do is first stop the container and remove it, because I'll use it in just a second. I'll remove the container, and what I will do is Docker allows us to link containers together. Once we have a single container there, we can point other containers to that container by linking them together. And that's how they will see each other. So what we can do for the other containers to see my initial container that contains zookeeper is I will just link them together to that first container to create a cloud cluster. How to do that? Again, we are allowed to use a command line here, which is very nice because we can just bootstrap. I provide a name. This is what we already know. And here is the interesting thing. Let me highlight that correctly. So I say --link, and I give the name of the container I want this container to be linked to. This, in our case, is the first container that Solr1, and I provide the zookeeper host not as a local host, but as the name of the linked container, the container that I'm actually linking to. Now, if I will run that container and check its logs, docker logs again, and I'll take that container, we can see that there were no other errors. We can see information about overseal election. So I think that something actually happened well. If we will go to tree and we'll look at the live nodes, we can see completely two different nodes here being present. So we have a cloud cluster running. We can check if everything is actually running by trying to create one replica for that particular collection. So what I will do is I'll use the collection API with the command add replica. It was executed successfully. And if I'll go to the graph, we can see that the shard that we created, actually a replica, is recovering, probably already did. Yes, so we have a working linked containers together that can work easily. However, let me now stop and remove those containers. And while I'm doing that, let me tell you what happens when I do that. So now when I'm removing those containers, the data that were there is gone. Because Docker actually is stateless. Once you remove the container, not stop it, but remove, the data is gone. And we not usually want to have that behavior because we don't like reindexing our data unless it's really necessary. So what we can do is we have two approaches to that particular problem. First of all, we can actually mount the container, mount some path and say, OK, Solr, use this path for the container as the container data directory, for example. And here we can see that I'm using a -v switch, and I'm mapping my local tmp/solr directory to a directory in the container called opt solr server Solr. This is a standard home directory for Solr. Let me now show you why it won't work. But this time, the command is proper. The thing is that Solr requires that solr.xml file to be in its home directory to be able to run. So if we would now run docker logs and specify that particular Docker container, we'll see exactly what Solr is missing. So Solr home directory must contain a Solr XML file. So let's stop that container. Docker stop. Let's remove it just for so we can reuse the same name. And let me create the Solr XML file here. I'll use a copy paste technique, very efficient one. And I'll just copy the solr.xml file contents that's usually used by Solr. That's not very relevant, but just to show you that this actually helped us run the container itself. I'll reuse the same command, so I'm not cheating here. And if I now go to Docker logs and specify that name, you can see that Docker started. So what Docker did is actually it will now write the data that it will now write the data into that mapped directory, so /tmp/solr. Again, not very useful. Maybe not that way. Again, useful, but that brings some challenges because the data is about the data locality. It lives here where we specified it to be mapped to. So I'll kill that container again, and I'll tell you a bit about what we can do as a second approach. The second approach is actually creating a Docker volume, which actually allows us to create containers that are stateful. Which means that this container, if I'll run a command like docker volume create, and I specify a name, and for example, size, like here, I can mount that container inside other containers. I created the container, and now I can just run those containers just like I would use another, Docker crashed. Great. So in general, minus volumes from would allow us, if the gods of demo would allow us, to run with minus volumes from, it would allow us to mount that given point, that given mount point to a container. However, it doesn't work right now. I can show you that in our booth, but let's skip for now. Sorry for that. And the last thing about the demo that we wanted to show you is something called Docker Compose. We can, of course, run all those commands manually and spin up multiple containers, spin up everything if we want. But we also are allowed to actually use a thing called Docker Compose, which we can define services, and they can be brought up automatically. For example, let me give you a very simple example of how the Docker Compose look like. I have a file called Docker Compose with minus Lucene Revolution YAML, but in general it should be Docker Compose.yaml, and I have definition of services here. You can see it on the highlighted fragment. So I have two services. The first one is Solr. It runs on top of an image with the version 6.2.1. It exposes to one port, 8983. It links to Zookeeper service. And during start, I would like to run a bash command, which is opt Solr bin Solr start in foreground with Zookeeper, with pointing to that linked Zookeeper container on port 2181. Next service is Zookeeper with a given image exposing 3 ports, the standard one used for Zookeeper to be able to communicate with each other and with the clients. However, I'll use a slightly more complicated example here. So I'll actually run 4 Solr services, Solr 1, Solr 2, Solr 3, just to show you how the linking works here in that case. First container is only linked to Zookeeper. Second container will be linked to Zookeeper and Solr 1. Third container will be linked to Zookeeper here, Zookeeper, Solr 1, Solr 2. And finally, fourth container will be linked to all the previous ones and the Zookeeper itself is not linked. Now, if I would run Docker Compose and say up, what happens is that Docker automatically spins up all the containers. They will be spin up here in foreground, so everything hopefully started. And this time, and if I would go to Cloud, Tree, and see live nodes, we can see 4 Solr's containers spin up automatically for us, so we can do that nicely without having to type in all those commands, worry about linking to know what's happening there. In general, Docker Compose is your friend. So now let me get back to the presentation, and we'll finish up during the rest 7 minutes.
Wink, wink. So yeah, performance results. We did some tests on Ubuntu with like just running Solr on it, running it on Docker, and running it on a VM, just to be able to test the performance. We had 2 shards and replication factor of 2, some data and some settings, obviously. And yeah, we didn't stress too much on tuning. We needed to get the out-of-the-box experience, so this is how it goes. First test was just Solr running on the machine itself. These were we were doing just indexing throughput test, and one was a combined indexing and also queries at the same time. When we ran 4 Solr instances on the same, so 4 Solr JVMs on the same bare metal machine, we actually got slightly better throughput. On a VM, throughput dropped considerably. Yeah, especially queries, right? Like a lot. If you look almost an order of magnitude. And then on Docker, it's somewhere in between. And we did those tests actually on OS X too. We got the same kind of thing, right? Bare metal performs best, VM performed worst, Docker was somewhere in between. Though it's not necessarily, I mean, if you want to do performance tests, don't do them on OS X because that's where you need that Docker needs that virtual machine, besides the fact that it kind of crashes because it's beta. But because it needs that virtual machine, you don't get that native performance that you get on Linux, right? Because Docker runs on top of Linux containers. But the rule of thumb is bare metal is faster than Docker, Docker is faster than VMs. This is kind of throughput CPU kind of performance testing that we did.
Okay, so getting back to how, not how now, but why, is that on bare metal machines or bare metal architecture, you can actually choose between one and multiple Solr instances. We did those tests on both of those OSs, and we've seen that multiple Solrs on a single bare metal machine compared to a single Solr but larger on the same machine, the multiple one seems to be faster. But that's probably because of the ability of splitting the load between and nice multi-threading. Of course, it's harder to scale. In a term that you need to over-provision, you need to buy the hardware up front, you need to know what you are actually expecting for, account for the spikes. If you don't have the hardware, you can't scale. You have full control over resources. You can go up to the driver level and tune everything you need. Noisy neighbors can appear, but not in a way like they do in the virtual machine world or containers. Basically, if you run multiple, for example, Solr instances of the bare metal, if one is using the whole disk or one is struggling with garbage collection, then it can be a struggle for resources for the others. And best or almost best performance out of the all that we tested. Why almost best? We haven't had a chance really to test the JDK with unikernels, but we've seen some tests on the web where I think it was for Cassandra. Yeah, Cassandra. And the thing is that the guys that did those tests were able to squeeze out more performance out of the VM and the unikernel running there than from bare metal. So
that was Cassandra on OSV, if you want to Google that.
Yes, so that's why we are bringing the unikernels topic here, because that's something promising, especially that Docker bought those guys. So we will probably see a very nice performance improvements from Docker itself in the near or further future. Then we have the VM-based architectures. Of course, very easy to put multiple on top of the hypervisor. Easy to scale, but requires some additional preparations, right? We don't have the Docker hub where we can just pull the images, the containers, and just run them. We need to do something to prepare. We have clear boundaries between VMs, so we can tune the guest operating system, but the guest operating system itself comes with an overhead, so we pay the price of being able to have the clear boundaries. And the thing is that we got the worst performance out of the all three that we tested. Finally, there's something in between, the Docker architecture. Very easy to scale if you have the ability to scale, actually. So until resources allow, very easy, you're allowed to actually maximize your resources usage. Easy to add constraints per container, so where you can limit the resources the container can actually use. Low overhead compared to traditional virtual machine because of no guest operating system. Native on Linux, this is the best performance when you can get out of Docker, as Radu mentioned, on top of OS X or Windows. It runs in a VM there. However, right now, already with the newest Docker version, hidden from the client, so it's nice we get the same experience, but still, this is not a truly native solution. Operations. I usually look like this when I'm dealing with operation stuff. So should you care about Solr tuning? We won't get into specific, but yes, you should when running inside Docker. Still, Solr is Solr. So keep in mind the environment constraints, like the amount of memory you gave to your containers, the amount of CPUs they are allowed to use, what are about the disk that lies there in the background for the Docker. watch out for those things like merges, memory issues, I/O subsystem, of course CPU garbage collection, and maybe prepare Solr configuration so that you actually use most out of your container. Then, should you care about Docker and think about it apart from it, that it starts your containers? Yes, you should. Docker has those, for example, notion of events that it emits, and we can listen to them. For example, this is a few events that that we are mentioning here for when Docker does something to the container lifecycle. And for example, when a container goes out of memory, we can spin up another one because we've seen that something was bad with the container itself, so it died, it's thrown out of memory, let's spin up another one. The nice thing is that those volumes that didn't work actually also emit events. So if we see that some container died and it unmounted for example, one of the replicas, we can automatically spin up a new container and to reuse exactly the event that was actually, the volume that was actually released and is now available without having to re-index the data or replicate it. We just will reuse the same volume. The key thing is Docker starts immediately, as we've seen, so it will be very quick for the container to be brought up. And as a last slide, almost the last, should you use Docker? Yes. When? When you need scaling. If you run one Solr on a bare metal machine, don't bother, because it's still some kind of something on top of the bare metal. You still need the Docker engine. It's still a bit slower, although as we mentioned, performance will probably go up in the future. If you need full resources utilization, then Docker is really great because you can plan and you can limit exactly what resources you want to limit to. Finally, if you have lots of nodes and you need to scale dynamically, look at Docker, look at containers, but probably with some additional tools, with orchestration tools like Docker Swarm, like Kubernetes from Google, or Apache Mesos, and they will give you a click-like experience to actually spin up hundreds of containers and manage dynamically. Thank you for coming here today. Thank you for listening to us and watching the demo. If you want to work with the stuff like we work here, come join us. There is a jobs listing on the Sematext site. If you want to have questions, I think we don't have time for questions. Come to our booth. We are downstairs. We'll be happy to talk with you. And once again, thank you and enjoy the rest of the conference.
Thank you.